Finally, in Chapter 2, we're going to talk about Section 12. The learning outcomes for Section 12 are to state the periodic trends of atomic radius, ionization energy, electron affinity, and electronegativity, and to use trends in these things to rank atoms based on those properties. So first, let's talk about atomic radius. The atomic radius is pretty self-explanatory. It is the size of the atoms. Now we have a figure here showing us that as you go down a family, the radius goes up, which makes sense because as we're going down a family, the value of n is increasing. Since n talks about the distance from the nucleus, the larger the n, the larger the atom. Now you can see here that as we go across a family, so from cesium to radon, the atomic radius tends to get smaller. Okay? And the reason for this is kind of counterintuitive. What's happening is as we go across a family, we're increasing the number of protons, so the number of protons goes up, the pull on the electrons goes up, but we're not adding shells. We're actually staying within a shell. Because we're staying within a shell, we don't have as many core electrons that are going to be shielding the pull of the nucleus. So we have what we call Z effective. The effective pull on the nucleus is equal to Z, the atomic number, minus the number of shielding electrons. And the number of shielding electrons are these core electrons. Okay, core electrons. As Z effective increases, the radius will decrease. So we can do a quick comparison of, say, lithium to fluorine. So the Z effective for lithium is equal to its atomic number, which is 3, minus the number of shielding electrons, core electrons. Well, let's take a look at the electron diagram, the electron configuration for lithium. It's 1s2, 2s1. So we've got 2 shielding electrons, so 3 minus 2. It has a Z effective of plus 1. But what about fluorine? Well, it's got 9 protons minus, now we need to take a look at its shielding electrons. So the electron configuration for fluorine is 1s2, 2s2, 2p5. So now, how many shielding electrons does it have? Well, it still only has 2 shielding electrons. So this is 9 minus 2, or plus 7. So these electrons feel like there are plus 7 charges in the nucleus pulling on that. That's going to pull those electrons in closer, and hence atomic radius decreases. This notion of Z effective actually explains all the rest of the trends we're going to look at except for one. So ionization energy. What is ionization energy? It is the energy required to remove an electron from a gaseous atom or ion. So if we pull an electron off, this is always going to be an endothermic process. It's always going to take energy. Now, we can pull one electron off, we'd call that ionization energy 1. If we pull a subsequent electron off, that would be ionization energy 2, and so on and so forth. Now, if we take a look at ionization energies, we can see that in sodium, the first ionization energy is 495 kilojoules per mole. But the second ionization energy is 4,560. Well, why is that? We know that removing one electron from sodium is very favorable. But once you start pulling out core electrons, that's when we start to see a large jump in our ionization energy. So magnesium has 2 relatively small ionization energies And then when we go to pull the third electron off, it jumps drastically. Okay? So, the trend in ionization energy is as you go down a family, ionization energy decreases. This is because as you go down a family, the atom gets bigger. The bigger it is, the easier it is to pull off. As you go across a period, ionization energy increases. Well, that really makes sense because on this end of the periodic table we have our nonmetals. And we know that nonmetals don't like to form cations, they tend to form anions. So it would make sense that the ionization energy would increase. Also, since the atomic radius is decreasing because of Z effective increasing, ionization energy will also increase. Electron affinity is our next trend. And electron affinity is the energy change associated with the addition of an electron to a gaseous atom or ion. Okay, so this is making anions. Now, usually, this would be an exothermic process. Some are a little bit endothermic. However, the point is that as we go down a family, electron affinity, EA, is going to decrease. And as we go across a period, electron affinity is going to increase. So it is just the opposite of the atomic radius, as is ionization energy the opposite trend of atomic radius. Electronegativity is not talked about in this chapter per se. However, I'm going to introduce it because this makes sense to introduce a periodic trend in with the periodic trends. Electronegativity is the tendency of an atom to pull shared pairs of electrons towards itself. Now, this is not a measurable value. This is a calculated value based on ionization energy and electron affinity and size and a whole bunch of other things. The point is, it does have a periodic trend. As you go down a family, electronegativity, which I write as E neg, is going to decrease. And as you go across a family, electronegativity is going to increase. Again, opposite trend of atomic radius. Now, that would make you think that culminating in group 8A, that would be the most electronegative. However, these guys are excluded since this is pulling a shared pair of electrons toward itself. These guys don't usually bond. Okay? So we kind of exclude the noble gases. That means fluorine here is the most electronegative atom. All right, let's use our knowledge of these trends to rank atoms. So, number 107 says, arrange the following groups of atoms in order of increasing size. So, A, we have tellurium, sulfur, and selenium. So, what we're talking about is tellurium, sulfur, and selenium. Okay, so we know that as we go down a family, the size is going to increase. So the one at the lowest would be tellurium, so that would be the largest. That means, if I read the question again, in order of increasing, that would mean that sulfur was the smallest, selenium would be next, and tellurium would be after that. In B, we have potassium circle potassium, bromine, and nickel. Okay, so they're all in the same period. We know as we go across a period, the size decreases. So that bromine would be smaller than nickel, which would be smaller than potassium. All right, and in C, the elements we're looking at are barium, ooh, that's a bad color for barium, there we go, barium, silicon, and fluorine. Okay, so fluorine's at the top and it's the farthest to the right, therefore fluorine should be the smallest. Silicon is in the third period, whereas barium is in the third, fourth, fifth, sixth period. So fluorine, then silicon, then barium. Let's do another example, and the example is 109 asked us to arrange atoms in 107 in order of increasing first ionization energy. So A asks us to do tellurium, sulfur, and selenium. So sulfur, selenium, tellurium. We know that as ionization energy goes down a family, it is going to decrease. So tellurium should be the least ionization energy, selenium, and then sulfur because of their relative position in the same family. Now, part B asks us about potassium, bromine, and nickel. So, in order of increasing first ionization energy, we know that as we go across a period, ionization energy increases. Therefore, potassium should have the smallest, followed by nickel, followed by bromine. And then finally, we have barium, silicon, and fluorine. So we know that ionization energy, as we go across, increases, and as we go down, it decreases. So the smallest should be barium because it's farthest to the left and it's lowest on the periodic table, followed by silicon and then fluorine. And finally, we're going to do electron affinity. So we're going to go from the least negative electron affinity to the most negative. Okay, so the least negative to the most negative. So the first thing we're going to look at is sulfur versus selenium. We know that electron affinity increases as we go across a family, and it increases as we go up. So the most the best way to say this is the lowest electron affinity would be for selenium and then sulfur. For part B, we're dealing with fluorine, chlorine, bromine, and iodine. Well, with fluorine, chlorine, bromine, and iodine, we're all in the same family. Electron affinity is going to decrease as you go down. So the least would be iodine, then bromine, then chlorine, then fluorine.